Good morning, everyone. You are welcome to today's lecture. Today we'll be talking about capacitors and dielectrics. In many devices, you must have encountered capacitors. They are basically electronic devices or electronic components that have the ability to store electrical energy. So the capacitors are known as devices that stores electrical energy. You must have noticed maybe at home when there is power outage, there are still some devices you connect to the electricity supply that will still power on for a while, maybe for a few seconds at home. There are many small devices in which when there is power outage, you'll still see some light indicators showing for a few seconds. That is capacitors at work. That means when power supply was available, the capacitor in that device stored electrical energy. And when there was power outage, the stored energy was now used to power up that light bulb for a while. And so we can liken capacitors to be like rechargeable batteries. But most times when we are talking about capacitors, they are devices that store small charges. So we can also liken batteries as capacitors. So since we'll be talking about capacitors in the sense of dielectrics, we'll be thinking about a capacitor as two parallel conducting plates, just like the symbol. This is the schematic symbol for capacitor right here. The schematic symbol for capacitor also tries to define it, where you have two parallel conducting plates. So these two lines are equal and they are parallel, unlike in a cell where you have one that is longer than the other. So when you have them equal and parallel, it's used to represent a capacitor. So when you have two conducting plates, then you can say you have a capacitor. Then you connect the wires to the two plates. They can store charges. As long as they can store charges, then we can call them capacitors. So they can store electrical energy. Let me be specific about electrical energy here. But the fact that this the parallel plates can store electrical energy, then we can call it a capacitor. So when we say a capacitor, there are ways with which we specify or describe the capacitor, and one of which is the capacitance. The capacitance of the capacitor tells us the amount of charge that the capacitor can store when it is connected across a certain potential. So when we are talking about storage of electrical energy, we must recall that we are storing charge Q. And before we store charge Q, we must connect it to a certain potential V. So the Q divided by V gives us capacitance. And we must always remember that let me take another color, that Q, which is charge, is measured in coulomb. V, which is the potential difference, is measured in volts. And now C, which is capacitance, is measured in farads. So the units singular is farad. So capacitance, when we know the capacitance of a capacitor and we know the potential difference across the terminals, then we can say the amount of, we can tell the amount of charge that the capacitor will store. And also when we are talking about a capacitor to be consisting of two parallel plates, there is still a physical parameter that helps us to relate the capacitance of that capacitor with the dimensions of the plates. The larger the plates, the larger the capacitance. This the parallel plates I'm drawing here is like the plates from the side view. When you are looking at the plate, it may be a rectangular plate, it may be a circular plate like your stainless plates. As long as they are, you have two of them, and you can place them parallel to each other, then we'll say that the area, the surface area of that plate, the larger the plates, the larger the capacitance. That means the larger the plates, the larger the amount of charge that will be stored per unit voltage. So also, there is also another thing we should also take into consideration, which is when we are saying two parallel plates being parallel to each other, the closer the plates, the higher the capacitance. When the two plates are very close to each other, you'll be having, when two plates are very close to each other, the capacitance will be higher than when the two plates are farther apart. Okay. So that means that when you have two parallel plates, this is A of the same dimension, and that set of parallel plates of the same dimensions, we'll call this A and we'll call this B. When the size of the plates are the same, then we can easily say that the capacitance of capacitor B will be greater than the capacitance of capacitor A. Let's move forward. So when we have two plates, when we have two plates like what we have here, we have plates A and plate B connected to an electrical power source, such that plate A is having potential VA, while plate B is having potential VB. Then easily we can say the potential difference between plate A and plate B will be VA minus VB. And from the last class, where we're talking about potential gradients, we were able to say something that looks like equation 2, where we were talking about change in potential and change in distance. So this is a relationship that relates the potential difference and electric field intensity. So when we know the electric field intensity to be, we have the potential difference to be VA minus VB, and we know the distance of separation between the two plates to be D. Then we can now say that the electric field intensity is the potential difference divided by the distance of separation between the plates. And we've also spoken about surface charge density. And now in these capacitors, we'll be talking about two plates, the surface area of the plates, the distance of separation. Since we are talking about surface area, it is convenient to talk about the surface charge density. So the surface charge density sigma, which is defined as Q over A, which we have defined, we've defined as Q over A, that is the charge divided by the surface area. Then coming trying to relate 3 to 2, equation 3 to equation 2, we can have equation 4. So equation 4, which is from equation 2, where we said we have E is equal to V over D. E here equal to V divided by D will be equal to Q over A. So sorry, I forgot to mention something here. The surface charge density rho is proportional to the electric field strength. So the electric field strength, as the electric field strength increases, the surface charge density also increases. So, and that, and the constant of proportionality from this gives us E to be equal to 1 over epsilon is the constant. The constant is 1 over epsilon, where epsilon is the permittivity of the medium. So from E equal to sigma over epsilon, we can easily obtain V over D to be our, just like we have here, to be our V over D. So, and like you have said, that capacitance C is equal to Q over V, that is capacitance equal to charge over potential difference. Then we can relate the potential difference we have here, say Q divided by the potential difference we have here from this expression 4. Let me clean the screen. From the expression 4, we can easily say that our potential difference V to be equal to sigma D over epsilon. And when we say C to be equal to Q over V, then we can come to say, and we know our V, then what is Q over V, which is C? You'll have equation 5. And we should always remember the relationship between epsilon R and epsilon naught. Epsilon naught is the permittivity of free space, and it is 8.85 times 10 to the power minus 12 farad per meter. Epsilon subscript R, that is epsilon subscript R, is relative permittivity, while epsilon is the permittivity of a particular material. So when we say, when we're talking about materials generally, they all have their permittivities, but that of free space is what is very common. And when we know that of free space, easily we can relate that of free space with that of any other material by the epsilon subscript R, which is the relative permittivity. So the relative permittivity and the permittivity applies to certain medium, while the epsilon naught applies to free space only. All right, free space. So the figure we have here looks like a capacitor, where we have two parallel plates. And since we have two parallel plates, electric field is set up between the plates. And when the electric field is set up, because the plates are connected to a certain potentials. And since they are connected to different potentials, potential difference is set up. As long as potential difference is set up, then electric field is set up. So we cannot talk about capacitors completely without talking about dielectrics. I've spoken about some basic things about capacitors. Number one is when we have two parallel plates, not just parallel plates, parallel conducting plates. The plates in this scenario are conductors, and we have two plates that are parallel, two conducting plates that are parallel. We can call such plates a capacitor. The larger the plates, the larger the capacitance. The closer the plates, the larger the capacitance. But once the plate touches, then it is no longer a capacitor. But as long as there is a space between the plates, we can call such pair of plates a capacitor. And in between the plates, there is air. Air is an insulator. So for the fact that air is an insulator, the nature of the capacitance of the capacitor would have a particular value because in between the plates, it is having air. When you decide to replace that air with maybe another insulator like nylon, when you fold nylon and you insert it between the plates, the capacitance will change immediately. The capacitance will change immediately once you replace the contents of this center. Let me get another color. When you replace the contents of this center from air, you replace it with another material, another insulator, another non-conducting material. So when you remove the nylon and you put paper, the capacitance would also change. And the capacitance will now not just depend on the dimensions of the plates, but will also depend on the contents between the plates, the nature of the contents between the plates. So once, and what about that nature? The permittivity of the material between the plates. The permittivity of paper is different from that of nylon, different from that of wood or sawdust or different, you have many, or plastics or anything. So, or glass, different materials have different dielectrics. So once you, so we can also call this a dielectric constant. The epsilon, we can call it a dielectric constant. So the epsilon here gives us information about, the epsilon here gives us information about the nature of the material in between the plates. And that nature also gives us the information about the capacitance of that capacitor. So the capacitance of the capacitor can be adjusted by the size of the plates, the distance of separation of the plates, and also the contents in between the plates. So let's talk about some theories of dielectrics. I've said before, dielectrics are insulators. That means they don't contain free electrons. Electrons in dielectrics are bound to the ionic lattice by electrostatic attraction to the atomic nucleus. One of the properties of insulators, anyway. When a dielectric material is placed in an electric field, electrons are displaced, just like when we're talking about charging, methods of charging. And we're talking about methods of charging. And we're talking about method, please, 1 minute, please. Okay, so okay, well, we're talking about methods of charging. And especially charging by induction. We spoke about having, let me get whiteboard. We were talking about methods of, we spoke about having a material consisting of positive charges and negative charges, equal number of positive and negative charges. We called it a neutral material. But when you now bring another material here, which is having excess of negative charges, and you bring another material that is having excess of negative charges, then this particular material will transform to something like this. The positive charges will be around here, while the negative charges will move away. So the same thing happens when you bring a non-conducting material in an electric field. In the electric field, you know, the electric field is made up of, in this case, is made up of two parallel plates at different potentials, VA, VB. So when VA is positive with respect to the negative, to VB, then you would expect the electrons to come around here. The electrons in the material between the plates to rush here, making it appear as if the positive charges are aligned in this way. So we should expect the charges in the material when we place a material, an insulator, in between parallel conducting plates, then we should expect the type of realignment we experience while talking about charging by induction. So let's move on. Each of the atoms in a dielectric material is said to be polarized. Yes, well, just like I said, well, you have a neutral material consisting of equal number of positive and negative charges. When you place such material in an electric field, then the electrons will drift to a side and the protons will drift to the other. Actually, it's the electrons that move. The protons only move slightly, but for the fact that the electrons have moved to a side, causing a deficiency of electrons on the other side, it will appear as if the protons are on one side, the electrons are on the other side. But for case of simplicity, let's say the electrons have moved to a side, the protons have moved to the other side. It will set up what we call a dipole, just like we've spoken about dipole, which is a system of equal and opposite charges. So you giving us a material that looks like this. Positive on the end, negative on the other end. And we should still remember our definition of dipole moments to be the product of the charge and the distance separating the charges. And so that means that when we have a material in between an insulator, when we have a material in between an insulator, the distance of separation between the blue plates, between the plates of the capacitor, would also be this distance A, since we have set up a dipole in between them. So we'll be applying that later on. So still on theory of dielectrics, the polarized atoms will tend to align in direction of electric field. This causes the ends of the surface of the dielectric medium close to the plates to become charged. So let's come back to this figure we have here. In this diagram, we have conducting plates A and B. A is having potential VA, B is having potential VB. Now we have put another material. So for the fact that we have set up A and B, we've connected them at different potentials. We would expect electric field to point in the direction from positive to negative, just like we have here. We would expect the electric field to point, this is E, this direction from positive to negative. We'll expect the electric field to point in this direction. So once the electric field points in this direction, it agrees with the properties of electric charges we said before. The same thing applies to this line. We expect this to point in this direction. So, but for the fact that we have brought in an insulator, before we bring in the insulator, let us draw the insulator here first. Let's say, let me take another color. Let's say we want to bring in this blue insulator. The blue insulator is made up of positive and negative charges. It's a neutral material. But once this blue insulator goes into this electric field, once it goes into this electric field, we will expect the negative charges to drift towards the positive plates, while the positive charges in this material to drift towards the negative plates, just like what we'll expect about basic properties of attraction. So the negative charges will drift towards the positive plate. So for that fact, another field will be set up. Another field will be set up in between this blue material that we are bringing in. And that new field is what we refer to as the E subscript delta. So E subscript delta will be the new field that will be set up in between the dielectric material. And that field would be pointing in opposite direction of the existing electric field between the plates. So as the electric, just like we have the electric field E in between the plates, pointing from positive to negative, similarly, within the plates, we will also have electric field pointing in its own direction from positive to negative, because we have a system of positive and negative charges now within that blue material. Then the direction of force will still point from the positive to the negative, and that means that the direction of its electric field will point in opposite direction of the electric field created by the conducting plates, created by the conducting parallel plates. So now we are having two fields, field E created by the conducting field and field E subscript delta created as a result of the polarization that was created in the dielectric material, created in the insulator that was put in between the plates. And one of the good things is that the electric field that is set up in between the dielectric material is related to the electric field that is set up between the plates. And that gives us to this relationship that says that the larger the field set up in between the material, the larger, okay, it should even be the other way. The larger the electric field, the larger the electric field set up between the plates, the larger the electric field set up in between the material. I would have preferred to have this written as E directly proportional to E delta, because it is E that determines E delta, not E delta determining E. So E delta, when we introduce the constant of proportionality in between E delta and E, we have a constant B, which gives us like polarizability. So it gives us the beta, gives us the extent of polarization that a material can have. So that this beta is connected to the material in between the plates. And this particular constant ranges from 0 to 1. When it is 0, it means that the material will not polarize, and it will not even affect the capacitance of the capacitor. Well, when it is 1, it will mean that it will be giving you infinite capacitance. Time is going, let's move further. So still on theory of dielectrics, let us consider two sets of capacitors, P and T. So let's say this is P, this is capacitor P, and capacitor T. Both of them are identical, meaning that the sizes of the plates are equal and the distance of separation between the plates are equal. So when it is connected, set up, when it is connected to different potentials, when the two plates are connected to different potentials, electric field is set up. And the electric field that is set up in P is EP, which is equal to the potential difference across the plates divided by the distance of separation. Similarly, in the capacitor T, the electric field set up in capacitor T is equal to the potential difference across the plates of the capacitor T divided by the distance of separation between the plates in capacitor T. We said the plates, the capacitors are identical. That means that the capacitance will be the same. The capacitance will be the same. The electric field will be the same. And all that for now. But once we introduce a dielectric in T, once we bring a dielectric and we'll put it in between T, then the capacitance will no longer be the same. The electric field setup will no longer be the same. But we can now find a relationship between the previous electric field, which is still what we have existing in capacitor P, with the current electric field, which we now have in capacitor T. And that relationship is given as ET equal to EP times 1 minus beta. And going further, by simple substitution and the likes, we have equation 8 and equation 9, all trying to relate the property of T with the previous properties in P. That is the properties in capacitor T with the properties in capacitor P. And the major new new quantity being specified there is the beta. So I suggest at your leisure you should go through and try to go through the slides and read what we have there. So still on the theory of dielectrics, assuming the two capacitors have the same charge Q, when we assume the two capacitors have the same charge Q, then we can say that Vp equal to Q over Cp. Just like we would have said that Vt equal to Q over Ct. The relationship between Vp and Vt is now what we have on the extreme ends of this equation. And going on and on, simple substitution, divide both sides by that, you can run down all this to equation 7. Like I've said about epsilon. Epsilon is equal to epsilon subscript r and epsilon naught, where epsilon is the dielectric of the material and epsilon r is the relative dielectric, which is the ratio of the dielectric of the material to that of free space. So one major point we should bring out here is equation 17. Equation 17 directly connects the dielectric constant with the polarizability. So the dielectric constant, when you from equation 17, when beta is 0, that means the epsilon r will be 1. Let me write it down. When beta equal to 0, okay, it's even here. I don't have to write it anymore. Let me just, when beta is 0, epsilon r will be 1. And when beta is 1, epsilon r will be infinity. So that means that when beta is 0, the dielectric you have put into that in between the parallel plates will make no difference. It will look as if it is still free space. It will not affect the capacitance of that capacitor in any way. But when the when the polarizability is 1, then you'll be having infinite relative permittivity, which is practically impossible anyway. So let's move on. So let's talk about, we've said capacitors store charges. So what is the amount of charges that they store? So let's consider a capacitor with two plates A and B and potential difference AV and VB, and the charges on the plates plus Q minus Q. Potential energy or the energy stored is given by QV. And when you walk around that equation, you can, by saying, when you say the energy stored equal to QV, and you remember that Q is equal to, sorry, no, sorry, I've missed something. Potential energy in electrostatics is QV. So the potential energy in electrostatics is QV, but the energy stored, we have to go through, we have to talk about the average now. We have to bring in an average, which will be, then we'll now say the energy stored will be half QV, where V is the potential difference. And when we remember that Q is equal to CV, then we can also get the other equation, which is half CV times V, which should be CV squared. And when we want to know the work done is also equal to the energy stored, which are given below here. So this one example, which is solved already. A parallel plate capacitor with dimension 1 meter long and 1 millimeter wide are insulated from each other by a cushion of air. That is, there is nothing, there is just air. The plates are just there. No nylon, no no oil, nothing, just vacant, occupied by air. And the cushion of air is 0.1 millimeter thick. Calculate the energy stored when the potential difference between the plates is 1 volt. So when the potential difference between the plates is 1 volt. So the first thing is, we begin by determining the capacitance of the capacitor. And so when we know the capacitance of the capacitor and we know the potential difference between the plates, then we can talk about the energy stored by the capacitor. So D, which is the energy, sorry, D, which is the distance of separation between the plates, we've been given as 1 millimeter. Sorry. Okay, so let's start with what is the area of the plates? The area of the plates will be the length. Where's my pen? The length times the width. The width is 1 millimeter wide. So then the area of the plates will be 1 meter times 1 millimeter. That is 1 times 10 to the minus 3. And that gives us 1 times 10 to the minus 3 meter squared. It's good that both units be in meter, so that we would have a uniform units at the end. So now we know the area of the plates and we know the distance of separation. The distance of separation was given by the cushion of air, because this cushion of air is 0.1 millimeter thick, which that is, we have 2 parallel plates. From the side, you can say the length of both plates is 1 meter each. When you look at it from the top, you'll be having something like this, where this will be 1 meter and the other dimension will be, let me put it here, 1 millimeter. Then that gave us the area of 1 times 10 to the power minus 3 meters squared. But the distance of separation, now we'll be looking at it from the side. So, and when we are looking from the side, that is when we should have what we have left on the screen. So when we are looking at it from the side, the distance of separation is the amount of air, the thickness of the air that we've been given, which is 0.1 millimeter. So that means the 2 plates are very close, 0.1 millimeter. Let's pen again. The distance between these 2 plates, 0.1 millimeter. And we have to also take that to meter anyway, and to know the distance of separation. So it's good that they all be in the same units. So from one of the previous formulas, though I did not really dwell on it, we can say that the capacitance of a capacitor directly proportional to the area of the plates, but inversely proportional to the distance of separation. And introducing the constant of proportionality, we can say capacitance of the plate equal to the constant of proportionality, which is dielectric constant, times the area of plates divided by distance of separation of the plates. Then we can now say that, fine, this is an expression for capacitance. We know the area. The area is 1 times 10 to the power minus 3 meters squared. We know the distance of separation, 0.1 times 10 raised to the power minus 3 meter. And we know the dielectric constant, epsilon. The dielectric constant, epsilon, is the permittivity of air. Permittivity of air and that of free space are very close. So we can just use that of free space and would have the same value. So and that gives us what we have been using before while talking about Coulomb's law, 8.85 times 10 raised to the power minus 12 farad per meter. So putting all that into the equation, we would have our capacitance to be 8.85 times 10 raised to the power minus 11 farad. And the energy stored, since we know the capacitance of the capacitance and we know the potential difference between the plates, then we can say the energy stored is half CV squared, as is 1/2 times the C, which we've just obtained, times V squared. The potential across the plates has been given to be 1 volt. And that brings us to the 1 square we have here. So capacitors can be connected in series or in parallel. And when we say capacitors are connected in series, they are arranged in this figure, like the way they are arranged in this figure, where we have whatsoever current that flows through C1 will flow through C2, through C3, and the rest. And whatsoever charge that is stored by C1 will be stored by C2, stored by C3, and the likes. So those are one of the basic. Okay, and finally, the potential difference across C1 plus that of C2 plus that of C3 plus that of all would, when you add them up, when you add the potential of across each of the plates, it will add up to the total potential supplied to the capacitors. So let me take that again. Capacitors, when in series, the same charge is stored in them, and the potential across each of them in series add up to give a final potential, which is the supply, which is like a supply potential across all of them. So the potential across each of them, that is, this V1 is the potential across C1 alone, V2 is potential across C2 alone, V3 is potential across C3 alone. But when you add V1 plus V2 plus V3, you will have the potential across C1 to C3. So, and the total capacitance is given by the equation below, which is 1 over the total capacitance. C total is 1 over C total equal to 1 over C1 plus 1 over C2 plus 1 over C3 on and on. Also, when capacitors can also be connected in parallel, and when they are connected in parallel, it means that the same potential is across them. These are these capacitors C1, C2, C3, and CK, they are in parallel. The same potential V that is across C1 is the same potential V across C2, the same potential V across C3, across all the capacitors that are in parallel. So regardless of the capacitance of the capacitor, the same potential will be across them. And the total charge that is stored is the total charge stored by C1 plus total charge stored by C2 plus the charge, the total charges stored. The total charge stored is the charge stored by C1 plus the charge stored by C2 plus the amount of charge stored by C3, and on and on. And the total capacitance can be easily defined as C total equal to C1 plus C2 plus C3 plus C4 to the last capacitor. So when we compare capacitors connected in series and those connected in parallel, we can say that in series, the total voltage supplied is equal to the summation of all the voltages of the capacitor, while in parallel, we say the same voltage is applied across all the capacitors. In series, we can say that the regardless of the capacitance, okay, let me take that again. In series, the same charge is stored regardless of the capacitance. The same charge Q is stored in each of the capacitors. The same charge Q is stored in each of the capacitors regardless of the capacitance. While in parallel, the total charge stored is the summation of the charge stored by each of the capacitors. In series, the total capacitance is taken as 1 over C total equal to 1 over C1 plus 1 over C2 and on and on. While in parallel, the total capacitance is direct addition of the capacitance of the capacitors. So this is an example that says, what is the effective capacitance of the combination of capacitors? To attempt this, these two capacitors, they're in parallel. Since they're in parallel, I can just add them up to, we'll have a new capacitor. These two can be replaced by a capacitance of 6 microfarad. Similarly, these two can be replaced by a capacitance of 12 microfarad, and it will lead to a similar circuit of this nature, where this is 6 microfarad and this is 12 microfarad. And the total capacitance in the circuit will now be 1 over C total equal to 1 over 6 plus 1 over 12. And LCM 12, 2 plus 1, 3 over 12, 1 over 4. Then the total capacitance CT will now be 4 microfarad. And the total energy stored in the capacitance will be half CV squared, half times 4 times 10 raised to the power minus 6, because it's microfarad, times V squared, that is 12 squared. So whatever you get there gives you the total energy stored in the capacitor, in the capacitors in joules. So in the next class, we'll talk about Ohm's law and the analysis of direct current circuits. On Thursday, which will be the next class, I will try to be available at 7:30 just to answer some questions. So So if you have some questions that you don't even know how to describe in an email, then let's meet at 7:30 a.m. on Thursday. So meet on Thursday.